Take a look at the next example in 14.1. We're asked to evaluate the double integral from 1 to 2 of 1 to x, 2xy plus 3y squared dy dx. So kind of what we want to do, almost kind of like an order of operations style idea, we want to start by doing the inside integral first. This integral is being done with respect to the y variable. It's going to be an integration dy. So we have the definite integral from 1 to 2. Let's work out that inside part. If we're going to integrate with respect to y, then we want to think of the function x as being constant. So I have 2x, and then the antiderivative of y would be y squared divided by 2 plus 3. The antiderivative of y squared would be y cubed divided by 3. And now we're going to evaluate this from 1 to x. We can do that using the fundamental theorem of calculus. Just going to plug in the upper bound and then subtract the antiderivative evaluated at the lower bound. This is the definite integral from 1 to 2 of everywhere I see a y, because I integrate with respect to y. So everywhere I see a y, that's where you're going to evaluate your bounds. So it's going to be x times x squared plus x cubed, subtract, and now I have to substitute in the lower limit of integration, x times 1 squared plus 1 cubed, and then we need to integrate this dx. This is the definite integral from 1 to 2. If we simplify the inside, this is going to be x cubed plus x cubed, which will give us 2x cubed. This is going to be 1 squared is 1. 1 times x is x. 1 cubed is 1. And then we have to subtract x and subtract 1. So now we have the definite integral from 1 to 2 of 2x cubed minus x minus 1. This is just a classic definite integral in the variable x. We can go ahead and find an antiderivative for this. Add 1 to the power, divide by the new power. Antiderivative of x is x squared divided by 2. Antiderivative of x of 1 is x. And then this is going to be evaluated from 1 to 2. Let's go ahead and substitute in our upper limit of integration. Also, to note that this coefficient would reduce to 1/2 x to the 4th. So I'm going to have 1/2 times 2 to the 4th minus 2 squared over 2 minus 2. And then I have to substitute in the lower limit of integration. 1/2 times 1 to the 4th minus minus 1 squared over 2 minus 1. And now we just have to kind of evaluate this. 2 to the 4th is 16, and then half of 16 would be 8. 2 squared is 4. 4 divided by 2 is 2. Minus 2. Minus 1 to the 4th is 1, times a half is a half. We have 1 squared is 1, minus a half will cancel, minus 1. So we should be left with the following. We have 8 minus 2, which is 4. Subtract 1/2 minus 1/2 cancels. So we get 4 minus -1, which is going to be positive 5. So the value of this integral works out to be 5. The term we give to something like we saw in example 2, this is what's referred to as an iterated integral. Integrated integrals are usually written in one of two forms, depending upon what the order of integration is. Remember, if you're integrating first with respect to y, then you can't have anything that involves y in those limits of integration, which would be the inside integration sign. A lot of times, especially in terms of notation, we don't write it like we did for the last example, but intuitively you think that there's like a bracket or a parenthesis here that separates like the two integrals. We have the inside integral, which is done with respect to the y variable. Once we do that, then we would integrate again, but with respect to the x variable, integrating dx. So as we said at the beginning of this chapter, if you're integrating with respect to y, your bounds cannot have anything that involve the variable y. But they can involve the other variable x, because when you're integrating with respect to y, we think of x as being constant. So the bounds here would be generally from a lower bound of some function of x, call it g1 of x, to an upper bound of some function of x, call it g2 of x. When we complete this integral, we will have integrated with respect to y, we will have then evaluated the y terms at some function of x, and this will give us a classic one-variable integral in the variable x. We can go ahead and evaluate that definite integral in terms of x, and then the numbers a and b that we plug in, those are going to be real values, and then therefore that will give us a real number output for this thing. The order could be reversed if you choose to integrate with respect to x first, and I see a typo already. If you integrate with respect to x, then remember your bounds cannot have the x variable in them. So these would have to be functions of y. So the lower limits would be from h1 of y to h2 of y, where h1 and h2 are functions of y. We would do that integral first. When you integrate with respect to x and then evaluate it at those bounds, that would produce a function of y. You then integrate that function with respect to y, and then you would plug in your bounds c and d. Okay. The inside limits of integration can be variables with respect to the outer variable of integration. However, the outside limits of integration must be constant with respect to both variables of integration. So it's always going to be the case that those last outer integrals will have numerical bounds. Okay. We can also kind of graph the region that's being discussed by these bounds. The outside limits indicate that x has to lie between 1 and 2. So if we look at our x bounds for that previous integral, x is going to go from 1 to 2, which would be from here to here. In addition to that, we also know that y has to lie between 1 and x. Okay. So when we integrate with respect to y was between 1 and x. So here's a height of 1. If you think of the function x, or y equals to x, that's just a straight line. Y-intercept of 0, slope of 1. And so the region we're looking at would be this region in here. It's between 1 and 2 for x, and then the y's would be between y equals to 1 and y equals to x. And so we would get a triangular region in this example. This is referred to as the region of integration that corresponds to that iterated integral. This brings us to the area of a plane region. In this section, we will find that the area of a plane region bounded by either a less than or equal to x less than or equal to b, and g1 of x less than or equal to y less than or equal to g2 of x, or it could be slightly differently. You could have y bounded between two constants c and d, and then x bounded between two functions of y. Let's call them h1 of y and h2 of y. We say that a region is vertically simple if the outside limits of integration with respect to the vertical lines x equals to a and x equals to b. If we look at this graph here, this is exactly what's happening in the first graph. The region itself, R, is bounded by two vertical lines. One is the vertical line x equals to a, and then the other one is the vertical line x equals to b. This is a vertically simple region. Similarly, a region is called horizontally simple if the outside limits of integration represent horizontal lines. If we look at this region here, the region is bounded by the horizontal line y equals to c and also y equals to d. So y is between c and d, and this region is going to be horizontally simple. The way this will affect the iterated integrals is as follows. When we have a vertically simple region, so if the region is vertically simple, then remember it's bounded between a less than or equal to x less than or equal to b. So it's the x variable that's bounded by constants, which means that that's going to be the outer part of our iterated integral, which means that the order of integration in that case will be dy dx. On the other hand, if it's a horizontally simple region, then the things that are constants that are bounding stuff are the lines y equals to c and y equals to d, and then once again that would be the outermost part of our iterated integral, which means that the order of integration is going to be dx dy. A lot of times if you place a representative rectangle in the region R, it can help to determine both the order of integration as well as the limits of integration. A vertical rectangle, as we said a moment ago, will imply the order of dy dx, with the inside limits of integration corresponding to the upper and lower bounds of the rectangle. So here, if we look at the function that's bounded above, that's g2, that's going to be the upper bound of the integration, and then the lower bound for the region would be g1. So that would go for the lower limit of integration. Similarly, if it's a horizontal rectangle, then the order of integration is going to be dx dy.